Another way we can represent our graphs is by using a 2D matrix. So how this basically works is we have a V cross V matrix, which is the size of the matrix is V cross V. Next, each row represents a vertex, which is in this case, like if we have 7 vertices, in this one we have 6 vertices. So we have like A, B, C, D, E, and F representing each row in a matrix. Also, each column is represented by the vertex, which is A, B, C, D, E, and F. So next, we insert values into the matrix by using this formula, which is if there is an edge between the from and the to vertex, the corresponding value into this vertex is going to be some value. Otherwise, it's going to be 0. So let's say if A and F are not connected, that means the value at this position, which is A and F, is going to be 0. Similarly, like A and E are not connected, so it's going to be 0. And A and B are connected, so the value is going to be 10. Similarly, like A and C are connected, so the value is going to be 15, which represents the weight. Let's say if this graph was not weighted, like this is for a weighted graph, but if this graph was not weighted, then we represent the value 1 if an edge is there between the from and to vertex, and 0 otherwise. So this graph's adjacency matrix would look something like this, which is we have total 7 edges in this, which is 1, 2, 3, 4, 5, 6, 7. So there are going to be 7 corresponding non-zero values into the matrix, which is we have this 10, 15, 60, 5, 40, 50, and 80. So we have total 7 different values. So how we can represent this in C++ is again using a 2D array, which is we can define something like int arr with the syntax, and this is going to have like v values, which is you are going to define memory for like v vertices where v is a constant. And we already know that we have the number of vertices that are given to us in the question, because most of the times when we are solving the problems related to graph, we are typically given like what is the constraint on the number of vertices. If there's not a constraint, we are going to see this next implementation which doesn't require the number of vertices, which means we can add vertices on the go. So an issue with this type of implementation, which is adjacency matrix, the first issue is you need to know how many vertices are there, because once you have defined a 2D array, like you cannot go back. Now, in the previous set of videos, we discussed the fact that you represent these vertices which have some labels. We convert those labels into integers, which is we again have like some map here, which stores a mapping of each of the labels, which is A is mapped to 0, B is mapped to 1, and C is mapped to 2, and so on, because the array indices are mapped to some values, which is in this case, each of the array indices have an integer value. They do not know like what the strings are. So whenever we are trying to access a location, something like uh, let's say if we are trying to change the number, this number 10, or we are trying to change this weight of a particular edge to some other value, you might do something like arr of 0 and then 1. But to get these values 0 and 1, which is we are decreasing the weight of this edge between A and B from 10 to 5. So you cannot do something like ARR of 0 and 1 equal to 5 because we still do not have access to this 0 and 1. So how we can map, like we can get access to this like value 0 and 1 is by getting the corresponding value in the map data structure. So typically our syntax for a labeled graph, like if it is an integer graph, like each of the nodes represent integers, then you can directly use the syntax. That's fine. But if it is not an integer graph, if it is a value based graph, which is it has some label that is a string, in this case A, B, C, D's, so you do something like ARR, and instead of passing the 0 and 1, you pass the map's name, which is like in this case, like let's call the map M. So we do something like map, and we pass A. In the second one, we pass M, and we pass B. So what this does is you can also do this in two steps, which is you calculate these in separate variables like int A or int B or int I and J. Like I prefer to do it directly because it's just like a mapping. So this M, A, and B is going to give us this value 0 and 1, and this translates back to this original array, and then we can retrieve these values. So let's see how we are going to implement this in C++. I have some code which I created last night, so you can check the link out. So this is not the graph API, but this is just a way to implement adjacency matrix. Excuse me. So we do not have to use like this particular way. Like there are hundreds of ways to represent this, but I'm using this syntax. You can try some other one if you'd like. Like you can even use vectors to do this. So typically, like when we have a graph like this, and let's say if you are trying to design some question, the input to the program will look something like this, which is you have a set of edges. Like even in your project too, we have the similar type of input. So we have the first number represents the number of lines or the number of edges that are present in the graph. The first column represents the from vertex, the second column represents the to vertex, and the third column represents the weight if it's present. So how we can like insert values in this graph like is using this syntax, which is I have this graph that I've created, which is a 2D matrix of size vertices and vertices, which is we just discussed earlier. And I also have this map function because right now we are dealing with some string labels rather than integer labels. So first we have to also create this particular mapping of A to 0 and B to 0, 1 and C to 2 and so on. So we are going to first read like how many lines are there, and then we are going to run a while loop that runs till the number of lines, or uh, you are where you are just decrementing the lines. Then you are going to read these values, which is you are going to read the three values that we have here, which is this is like from, to, and wait. Like you can do the parsing. Next, what we are going to do is we are going to insert this from and to into the map if it is not already there, which is our map is called mapper. So I'm just calling this M right now for the sake of brevity. So we have like M, and we are going to insert this from if this from is not already there in the map. And we are going to also insert M of 2 to a new number, which is I have this number like j equal to 0. So first we are going to check whether the from and to vertices are already present in a map, and I'm going to show you like how to check that. Next we are going to add some value here, which is if from is not there, you're going to assign this value j, where j is like 0 initially, and after every insertion you are going to also insert the value. So you can do this in multiple steps. I prefer to do it in one step, like I'm going to show you in the next slide. But you insert the values. Next, you are just going to use the same convention, which I just described here, to change the value to weight, because it's pretty simple. So if this was a non-labeled map, which was if the labels were just zeros and ones, it would be just one line of code, which is just ARR of 0 and 1 is going to be 5 and so on. But since this is a labeled map, we might need to do some extra work. So this is the exact code. What this does is in this line, which is you're first reading the from, to, and wait values, you are checking whether our from vertex already exists in the map or not. So this syntax, which is mapper.find, the find function belongs to the map class. And if you do like mapper.find from, this basically returns an iterator to the from vertex. So if the from vertex like this, let's say if we are trying to like if we read something like G, where from is equal to G, and if mapper.find is going to check like whether G is there in our map or not, where from is the key in the map. So this is the set of keys, and this is like the right ones are the values. This will return an iterator. So let's say if we are talking about G, since G is not in the map, it's going to return an iterator which will be equal to mapper.end, which is like the mapper.end returns an iterator which is pointing to the end of the map, which is there's nothing in the map. So this syntax tells us that the value is not already existing in the map. So we add this value, like called some arbitrary value like J, which was 0 initially, and we increment it, which is like, let's say if we have now a new vertex, we are going to increment that value. Similarly, we are also going to insert the end vertex, which is if the vertex is not already there, we need to have the mapping for that as well. Because if you miss this step, which is the second one, it's going to create a lot more problems for questions which are directed and look something like this. Like, let's say if there are just two values, so the graph will never know that there is a B vertex that is present if we do not uh, do this step. In the next step, we are just assigning the value of weight. So this is basically hidden, but like it's equal to weight behind my picture. So what we just did was we inserted the value weight at the mapper from and mapper to. So mapper from, like talk about the first row. So how this is going to work is, let me just choose some other color. So how this is going to work is, in the first statement, we have A that maps to from, B that maps to 2, and 10 that maps to weight. Next, we check mapper.find is equal to mapper.find A is equal to mapper.end. So since there's nothing in the map, like initially we'll have an empty map, this is going to return true. So we'll add a new thing to our map, a new vertex to the map, which is called A, and we are going to assign the value of 0, and J is now incremented to 1. Earlier it was 0, now it's incremented to 1. Next, it's going to go to this line. It's going to check mapper.find 2, which is like whether the 2 vertex is present in the map or not. So the 2 vertex is not present right now. So it's also going to insert the value B. It's going to add the value J equal to 1, and it's going to increment J to 2. Next, in this statement, what it basically does is it it first calculates this inner value, which is mapper of from. So mapper of from is mapper of the A value, which is mapper of A. So this is going to return the value 0. Next, mapper of 2 is going to return the value 1 because there's a one-to-one mapping of B to 1. So the corresponding location in our graph, which is initially everything was 0, right? Because we defined a new matrix. So it's going to change that to weight, which is weight is 10. So at location 0 and 1, which is 0 and 1, we are going to change this to the value 10. So 10 will be inserted. Similarly, like after this, we'll go back to the loop and we are going to insert more values. Now, how we print like adjacent values, you can see that like in the code here. I'm not going to discuss, it's like pretty trivial. Also, you are going to implement all these things in your like there's a static problem as well as in your project you are going to implement this. So like adjacency matrix is typically implemented in a 2D array. Like the general structure, it's a 2D array. There's not much flexibility. Like you shouldn't be using something like vectors or like some other values. Typically it's implemented by a 2D array, so like that's fine. But in the other forms of representation like edge list, or we are going to discuss adjacency list very soon, you can represent a lot of different types of uh, different STL data structures, which include like vectors or different forms of lists and stuff like that. Now, one thing I want to let you know is like this map function, theoretically, this has a complexity of O of 1, which is like, let's say if I want to find out what is A's value, if I do something like map of A, I can insert or I can find out what's the value in O of 1 time theoretically. We are going to discuss much more about like maps and like why like O1 doesn't make sense and like in which situation in the next week, like next to next week when we cover maps. But for now, you can consider like you can get the mapping in just O of 1 time or constant time. So let's discuss the performance of the map data structure, which is we covered now the entire maps. So how can we find like connectedness in this case, which is, let's say if I ask this question whether A is connected to B. Now since I told you like the map has constant access, or forget about this map, like let's say if these nodes were representing by zeros and ones and so on, I'm just taking some random numbers. How can we check whether like 0 is connected to 1 or A is connected to B and so on? So just pause the video and think about like what would be the time complexity of connectedness and what would be the time complexity of adjacency, which is if I want to find what are the nodes that are adjacent to A. So I hope you have like written something on a piece of paper. So the first one is connectedness, and you can find out like whether two nodes are connected by just doing something like ARR of A and B, where A and B are the values of the vertex, or if it is an integer map like integer graph, like the values have integer values, then you just do something like ARR of 0 and 1 and so on. Or even if you use a map, it will be just like O of 1. So we can find that like by just using something like whether this value is not 0 or not. So if that is 0, that means they are not connected. If that value is non-zero, that means they are connected. And this is going to consume like O of 1 time, because arrays take constant amount of time to go to a particular location. What about adjacency? Like what are A's adjacent nodes? So to find A's adjacent nodes, you still have to go to the row of the from vertex, which is you do something like ARR of 0, and then you have to traverse this loop to all the vertices and check whether each of the vertices is 0 or not. So this will take like V time, because the number of columns in this matrix are going to be V, like because it's a strictly 2D array, so it's going to take like V amount of time. What about space? So the space is really straightforward. This is like O of V square, because it takes like V rows and V columns in the matrix, so it's O of V square. We have improved a lot on this connectedness component, as well as we have also improved a lot on the adjacency component, because right, like when we discussed edge list, this was something like O of E and O of E for the adjacent nodes as well. And when E tends to become something like V square, which is we have a very dense graph, these operations were very costly in edge list, but now they have been reduced. Now, this way of representing maps, of representing graphs in the form of adjacency matrix works really well for dense graphs, which is if they are connected and we have a lot of values in this matrix, this is the best we can do. In the next video, we are going to discuss the next form, which is it's called the adjacency list implementation. But before that, like I'll just reveal the answers which we just discussed, which is A connected to B? That's going to take like O of 1 time. I just mentioned that to you. And the other one is going to take O of V time, which is like if you want to find A's adjacent nodes. And the space, now it's going to consume much more space because we have to store like a lot of data in the form of like v cross v matrices, v cross v matrix. And we can also see that there's a lot of wastage of space because there are so many zeros in the matrix, like while the number of edges are so few. So that will give us a good segue into the next form of data structure, which is we are going to collapse like all these zero values. What if we just remove all these zero values and just store the non-zero values? So we are going to discuss the next one, adjacency list, in the next video.